presentation gets uploaded.
Is it? Do you hear me?
Yeah, can you hear me?
Yeah. I don't know, but I had some.
Okay, I'm looking forward to the present for scientific view. Actually, we have had cool questions. Great, we was eager to gather great data, and also we was trying to develop powerful tools to deal with that data. Actually, we have actually the first and the second steps. We have a lot of cool questions from before. Now we can get a lot of great data in terms of amount of and quality, and also we are trying to develop those powerful tools. Developing those powerful tools is data science somehow. So we will be happy if we can aggregate all together these three. In cosmology and astrophysics, from data observational point of view, actually CMB was one of the most important and influencing observations we could have actually accurate cosmology. And the beginning of the precision cosmology was somehow with some observations, including CMB. And the amount of data in astrophysics and cosmology is getting much bigger every year. As you can see, the amount of data per night we could gather was about 1998 was about 10 gigabytes per night, and it's getting more and more. For just one telescope, it's getting to 90 terabytes per night. So, and the number of observatories are getting larger. So we have to deal with a huge amount of data. Okay, these are some examples of the observatories. They are developed, or they are getting developed to. They are getting prepared to gather data, and there are a lot more. And in terms of how much, because we to deal with that amount of data, we need to we cannot use human anymore, so we need to use machines because they doesn't get tired. So, and they are more accurate. The performance is somehow constant. So the first thing comes into mind when you go to use AI or different aspects of machines to do jobs for you is machine learning. To show that how much machine learning is getting more important, I just it's only searching in the abstracts of the physics section actually of the archive, so you can see that the number of appearance of the term machine learning in the abstracts is logarithmically actually exponentially higher and higher. So the field is getting hotter, so it's a good place to invest and to set your future directions in. It's for just as a very brief introduction of what is machine learning. If you have a two-dimensional data set including red and these blue points, you can and I say that if you can see the pointer, I say that if I will find one data point here, what class you will specify to you will choose to what class to this data point to be a member of that class. You certainly will go with the blue points, the blue class. So what you are doing in your brain is somehow making a model between these two areas and try to specify a region for blue dots and the blue dots and reds, and we can expect machine do the same thing for us by finding the best, for example, line here, and for this line we have two free parameters. Just the only thing we need to do is finding the best parameters, which here is a and b, to find this line. And in the hyperparameter space, which is which includes a and b, we need to find some kind of optimized region to which indicates the best line which sets these two data sets. So the whole machine learning idea and the whole machine learning procedure is somehow optimization of one problem that that points into your desire. So you need to find the best thing you can optimize it, and then you have the goal somehow. These are some examples of a bit more complex data sets, and how machine tries to find the red and blue regions for these points through different mathematical models, because you can use not just the simple line. You can use a lot of different mathematical models. You have infinite number of models, so you have a lot of different machine learning algorithms. You can see that everyone is doing somehow better or worse jobs in different problems. So the thing you need is to find the best machine learning algorithm to deal with that specific problem. And a lot of works that people are doing out there is about I've tried this algorithm, this, and the next person is going to say that I've tried that one and I've find the better results, and so on. The most machine algorithm, the problems are you can divide the whole area somehow to classification and regression problems, where classification is when the example we have seen actually is about separating data into two different clusters or classes, and when you have continuum target to be predicted, you can aid with regression. And both regression and classification are sub sections of the supervised learning. You have another branch of machine learning, which is unsupervised learning, which you don't say the machine to and you don't expect machine to train on some labeled data, because in what we have so far, we know for a part of data, for a small portion of data, we know the exact labels, and we let machine to get optimized on those labels. And what if we don't have labels? We need to say to machine that try to find the best clustered points of the data which are you can unsupervisedly separate the data and let us know how you think actually how machine thinks about the data separation. Here I try to get to present a very brief review about what people have done using machine learning in astrophysics and cosmology. The most famous and ancient problem in cosmology and astrophysics is trying to classify galaxies and actually astronomical objects, the type of them. So we can start with classification. One of the most famous challenges in that is Galaxy Zoo. You can search for that. There are different versions of it. You can find a lot of sample codes to try that, and it's a good start if anyone is interested. And another application in classification is when you have, for example, observation or station in some kind of some kind of field, and you need to classify the largest structures in terms of properties to being domain walls or void halos or different things in that simulation. Then we can go to detection, which people try to find objects in, as an application, people try to find objects in large images, because previously we have an image which includes, for example, 1,000 objects, so people could request, people could ask for images or anyone to find objects. But now we have, for example, millions of objects in one image, so it's impossible to ask people to do that, machine to find objects. And for next application, okay, where is the next slide? 20. Can you hear me? Okay. I guess there was a lag in maybe my internet connection. And actually, these are different results I have done. If you are interested to search about them, I will share this presentation. You can find different studies about this subject. Data cleansing is the next application I will talk about. You can actually there are a lot of undesired phenomena in the observation, so we need to find and remove them. RFI is one of them, which in radio telescopes there are a lot of radio emissions on Earth we don't like them to be in the the cosmological observation. Also, in another study, people have tried to remove the dust from CMB. Actually, the result here is very amazing. I was very amazed when I see that results, and deep learning reduced this dust from CMB and produced the original map. And there are a lot of other applications you can go for them. And in terms of simulation, actually deep learning and machine learning is able to try to learn about some concepts you have been producing before, and learn about the concepts and try to reproduce them. These are the paintings. Actually, machine have tried to learn about a lot of paintings and produce these paintings. All of these paintings are produced by machines. And these people, actually celebrities, the first row is produced by machine, and the second row are real human, actually. And it's very amazing to know that the first row, it doesn't even exist anywhere. You cannot find them. They are totally simulated by machines. So we can use this feature of machine to produce and ask machine to help us about our simulations, because we know that if anyone have any experience with them, there are of functional consumption, and it's a very time-consuming process to simulate anything in true n-body simulations. So, and you can see that a machine could replicate the statistics of the simulations very well. Also, there are a lot of different studies on that as well. You can try to look for them. Actually, this is an animation because it's PDF. It doesn't run. You can look for this paper, or in painting. Using deep learning to inpaint some pictures, you can see, I guess you can find this animation, which is try to remove, erase some part of this image, and machine will fill them with the most probable things to be there. So we can use that kind of, actually this is another application of that. We can use this to fill when we miss the data. there are a lot of regions we are interested to observe, but there is something in the way, and we will miss a small part of that image maybe, for example, and we can ask machine to fill that region with the most probable things to be there. So there is another application. Actually, I have a recent paper on that. You can search and find it. It's to impede CMB maps, and this is another application. It's very amazing. You can look for this paper, which people have tried to impede this face on some actions of another person, and actually you can see this on YouTube, and Mona Lisa literally will talk to you. And for the last application, I will go through the anomaly detection, which is the idea of this, the main idea of the subject of this talk. In anomaly detection, you will try to find the most anomalous thing in a very big data set, and because it is either very interesting or it's should not be there, so you should remove it to have a better quality of statistical analysis. So there are applications for I ask you to not 60 seconds, 10 seconds to think about this image and find the most anomalous face in this image. I guess you will find this one as the most anomalous pumpkin. Actually, if there was something here, for example, let's say with less green hair on the pumpkin, you may mention this one or this one, but it's not. So being an anomaly could be in different aspects. So you may think something as an anomaly, and your friend does not think that one as an anomaly and find something else, because your way of thinking are different. So we need to deal with this problem, and this is a conceptual problem. So we cannot accept machine to different machine learning algorithms or anomaly detection algorithms to say always something similar or something constant when you want to try to find a. And it's important to know. And in one study, people actually, Raynoris said that in different years of the very major astronomical discoveries, the number of serendipities are very larger than the predicted observations. When you plan to observe something, you have some plans. You predict I want to observe that one and try to statistically analyze that and have those results maybe something else. But there are a lot of unexpected events which are very fortunate, and they call them serendipities. And if you find them, you can maybe win a Nobel Prize. So if you see in this table, you can see that for example, in Hubble Space Telescope, the key of the project, which was in the main plan, was these three. These are planned to be achieved by Hubble telescope, but the one which won the Nobel Prize was not even planned, which is the power energy. And the highly cited, the two of highly cited, actually the most seen results of the Hubble Space Telescope are not including in the two of out of three are not included in the plan. So I put these two slots to say that anomalies are important, and you can go for you can look for other studies in that area. And it's not very busy. You can enter this area because there are a lot of things to do. And in one of the makers of the A telescope. In the 5 of them, one of the most important of them is anomaly detection, which they have tried to they introduced these 2 challenges to encourage people to work on this problem. And the drama paper is a result of this concern. So we have tried to actually the free lunch theorem is what I said earlier. It's somehow that you cannot accept machine you cannot expect machine to produce to be the you cannot expect machine learning algorithms to find the best algorithm to do well on every problem. So there are different algorithms. Each of them can be good for one problem. And drama, the drama idea is about letting people to have a hyper algorithm, a meta algorithm, not just one algorithm, because in drama you will use dimensionality reduction to data into a very lower dimension, lower the dimension of data, and then cluster them into different clusters and find the most anomalous data which are far from these clusters. For example, if you have some images from the handwritten digits and you find one data point in the reduced in the latent space, which is the dimension reduced, here you will say that it is an anomaly. And the whole idea, the whole scenario of the drama is that when you have a data set, you will reduce it into a latent space and you will cluster them and you will find the most anomalous data in respect to those clusters. And in each time you use drama, you can split the data into different shapes and find the main shapes of the data and try to calculate each data point distance from these main shapes.
Alireza, you have
Yes?
5 minutes.
Oh, that's very good. That's very enough.
Thanks.
And so for drama, you will need to pick one-dimensionality reduction technique, which are not just one. You have a lot of options. I have added some more recently, so there are a lot of options. For clustering method, we have tried different clustering methods. The best one was agglomerative, so you don't have to choose one clustering method, because I can recommend you choose the agglomerative clustering method. And if you want to calculate the distance between the main clusters, the main shapes, and the anomalous data, you need to define some metrics, and you need to define the distance. And so you can use different metrics. We have option here. So the problem is we have different options. We have to choose the dimensionality reduction method and the metric. We have 10 metrics and 5 dimensionality reduction method. So we have 50 options. There are different options, and this is the difficulty with drama. And because of that, drama is a meta algorithm. It's not one algorithm. We try to benchmark drama through different data sets. These are simulations, and you can see the anomalous data is when you have a bump in a data in the time series, and we augment them with noise and some scaling and shifts. And there are some real data sets, including some cardiac data, cardiographical data, and in different aspects of nature. You can try. If you go to the paper you can find these data and read about them. But these are real data sets. We didn't simulate them. We have used 3 kinds of metrics. AUC, if you're familiar with MC, and RWS. The difference with RWS is if something is anomalous and it's very anomalous, it's important to put that on the top of the list, because the anomaly detection method will receive the data, your data, and it will give you a score to being an outlier for each of your data. So if you give your anomaly detection method, for example, 100 data points, it will return you 100 scores, and those scores mean each data, how much one data point is anomalous. So higher score means it's very anomalous. Less score, it's less anomalous. So in RWS, it's important for the most anomalous objects to be on the top of the list. It considers the rank, actually, rank weighted score. The RWS stands for that. For the result, you can see that because the blue color means drama win, wins, yes, and the yellow colors means the other algorithms we have tried to compare drama with wins. You can see that drama can win a lot, in different data sets, but the problem is that we need to specify a dimension interaction method and a metric each time, so it varies into different data sets. And also we compare drama versus local outlier finder and iForest. To deal with that problem, data into train and test, we assume that you have a whole data set. You go through a very small portion of that data and find just one anomaly, and say to the anomaly detection method, try to find something similar to this one. And if you find more seen outliers in that small portion of data, your method will work better. So we'll let drama and local outlier finder and iForest to see some certain outliers more and more, and the performance getting better every time. But you can see that drama is best, and drama could return the anomalies better than the others. And in different cases, when you have this kind of simulation of anomaly in low dimensions, and the new class, which is another scenario of our simulations, again in low dimensions, and you have drama to be the best in high dimensions as well. And for the simulated data, you can see drama is as good as iForest, where for this one, drama was as good as LOF. So we could conclude the drama to be very robust. So that's it so far. Thank you for your attention. You can find drama here.
Yeah. Thanks a lot. Thank you for the nice talk, Alireza. We have time for a couple of short questions. Since we already ran out of the time, so please write your question or raise your hand to ask your questions. Any questions?
Good.
May I ask a question?
Okay. Yes. Sure.
Thanks. You see, well, we have a lot of data for CMB, for example. So your method can determine what could be thrown out and what could be kept. Yeah, because I'm a theoretical. I don't know much about these things, and it's always a question to me. How could we determine which is important, which data point is important here? Thanks.
Actually, thank you for the question. Actually, the idea of anomaly detection is not to determine because something could be an anomaly and could be a bad anomaly, which is, for example, that day is something happens and your receiver doesn't work and something happens. So it isn't bad anomaly. So you need to throw it away. And in another scenario, there might be something happens and you are interested to detect that thing, and it was in a very short period of time, so, and you will miss it if you don't see it. So an anomaly could be a bad thing or a good thing. The main responsibility of the main goal of anomaly detection is to find them. Then you can decide you want to keep it because it's very interesting, or you want to throw it away because it's just ruining your data set. I'm not sure if I could clarify it.
Thanks. Thanks.
Okay.
Alireza, do you see the Pavel's question? I can read it for you. Pavel asks, I would like to ask, has the data mining of cosmological observation indicated how large the density contrast between different regions is? We have, e.g., we have the Keenan Barger void in 400 megaparsec radius, significant matter under density. Do you see the question? Alireza, do you hear me? Puri, I don't hear Alireza.
Yes, yeah. I'm not sure why I got muted. I do that.
Do you see?
Sure,
do you see
actually.
The question?
Yes. You can find them, but about how it happens, you need to make a scenario in theoretical physics, because the data mining will help you to find anything which is anomalous or you are interested in. You can train it to find them. But why it is here is still our responsibility to answer. I hope machine go for that in next few years, but machine is still not able to answer those questions.
Pavel, did you get your answer? Seems that Pavel, are you satisfied with Alireza's answer? Okay, it seems that Pavel is satisfied. So let's finish the session right now. And now it's the time for the lunch break, and we will be back at 2 p.m. Please be on time for the next session. And Hossein, do you have any remarks or announcements for the audience here?
No, I just want to thank you for chairing this session, and we will start on time.
Thanks. You're welcome. See you. Bye.
Thank you. Cheers.
What about the group picture? It's good question. Do you have any plan for the conference picture?
We will ask people to share the webcam at the end. I mean, maybe in the break at afternoon. We will ask people to share their webcam as much as possible. So we just